Okay. Let's see. Okay. Ba-ba-da. So, today is going to be a shorter one. I probably have to finish up around 45. But we'll have plenty of time to look over our Anki cards, and then also have plenty of time to then go over our the test. Okay, so I think we'll just go ahead and get started. There we are. Sure that works. Okay. Sweet. So let us get started. Oh, we need a little bit more zoom. I'll be learning that. Okay, local extrema. Okay. So I'm pretty sure. Let's see. Okay, so the local extrema are you find them through taking the the second order derivative and finding all spots where the second order derivative is 0. And what that means is that, or rather, when the second order derivative is 0, is that our rate of change has unless there are, like, it's an odd function, like that there is no rate of change, right? Where that would be 0, right? But in functions that are like normal, that have rates of change, if our second order derivative is 0, it means that our rate of change is 0 at that point. And we know that when, like, if you could think of like a bell like a normal bell curve, at the top of that, like, there's going to be a slope of the tangent line at some point where it's 0, right at the very top, because it was the rate of change was increasing to this point, and then it began decreasing, right? And so we find 0, and then let's see, find the derivative. Oh, okay. That's not it. Womp womp. Okay. We have to find critical points. Okay. Okay, that makes sense, because the first order, when the rate of change is 0, there are like a critical point, which makes sense. Where it flip-flops, and then what I said with local minimum, or okay, yeah, I think we'll just go for it. So send that one through. Linearization. This is using the slope of the tangent line as an approximation of the function. Okay, a rational number is one in which, or can be expressed as a ratio of two integers. Irrational numbers cannot be expressed, additionally, rational numbers can be infinite, but they have to be repeating. Irrational numbers cannot be expressed by a ratio of two integers, and they can have non-repeating infinites. Yep. Okay, sweet. Okay, how do you express areas under the curve as the limits of Riemann sums? Okay, so a Riemann sum is where you take like rectangles to approximate. Like you take rectangles. Say we have 4 rectangles, and we use the 4 rectangles, and we approximate, or we adjust their heights such that it is an approximation of the area under the curve, right? And then at this point, you then take the limit as the number of rectangles approaches infinity. Okay, so I gave a conceptual. We will be learning more about this one, so I'm fine with pushing this one through. The leading coefficient is the coefficient that has the highest degree. Local extrema, first you find critical points by evaluating the first order derivative at 0. And then at that like 0 point, at those points, and then you take the second order derivative, and then at the points, the critical point, and you input the critical points. If it's less than 0, it's a maximum, and greater than 0 is a minimum. It's less than 0, it's a maximum. Greater than 0, it's a minimum. Okay. Okay, yes. Okay. I feel good about that. So y would evaluate to 0. Yes. Okay, we finished. Nice. Okay, so now we'll just head over to the test and keep working through that until we're done. Okay, so I think I'll just increase. Actually, no. We'll need Anki. Calculus. Okay, so I think we're at the very bottom. Okay, if I'm remembering correctly, I was wanting to dive into something before. Okay. Oh, okay. So we want to figure out what it means for a function to be bounded. And then also, my horizontal and vertical asymptote answers were only for rational functions. And so I need to have, because that's sort of just a rule of thumb, right? So I need to have one that is more, or rather, one that also describes for non-rational, for functions that aren't rational. So actually, I don't want to revise. I want to create. Actually, I do want to check if I did specify. Okay. Yes, for rational functions, slanted asymptotes. Oops. Okay. Functions that Okay, so are there functions that aren't rational functions that have slanted asymptotes, or is this rule, which seems to be specifying the conditions for a slanted asymptote for a rational function? General enough? Or rather, function, or is this rule the only way in which we have slanted asymptotes? Okay, so I think on the general case, I think it is safe to go ahead with what we're seeing. So it says slant asymptotes are mostly associated with rational functions, but other types of function can also exhibit slant asymptote-like behavior, though it's less standard and depends on how we define slant asymptote. So I think we're actually okay with this. But I do think it is the case that for horizontal and vertical, our current definition is insufficient. Okay. Okay, so let's just go ahead and continue. Okay. How do you find a horizontal asymptote? Find horizontal for non-rational functions. Oh, genius. Yeah, that totally makes sense. Okay, to find the horizontal asymptote of a non-rational function, just compute the limit to infinity, and if the limit at finite value L, or is finite at value L, the horizontal asymptote is y equals L. Analyze each direction separately for piecewise or complex functions. Okay. Okay, so for this one, we're looking at a finite L that, at a finite X, Y approaches infinity. Yes. Oops. Okay, perfect. So we have that. Now, okay, in the context of calculus, could you describe... Oh, actually, I do not want... Oh, no. If its values are confined within some finite interval for all x in its domain, or a specified interval. Okay. Okay, so for all x in its domain is bounded if its values are confined within some for all x in its domain. Okay. Okay, so so in calculus, a function is bounded if its values are confined within some finite interval for all x in its domain. Oh. For all x in its domain or a specified interval. Okay, so now I'm going to make a hypothesis. So I think there are two situations wherein we could have a bounded function. Well, I guess I'll specify at least two, right? Because there's probably more, because I do not know loads of math. But so one situation, I'm assuming that for some okay. So for all x in its domain, we're going to be landing within some finite interval. So I guess I've found three possible functions. So one function is one wherein we have a horizontal asymptote. And so as x approaches infinity, we aren't going to have, we're going to be bounded. Additionally, you could have a piecewise function that merely returns a value instead of doing anything with it, right? Or rather, any function that just merely returns a value instead of doing anything with it. And then, let's see. So, like, for example, f of x equals 6, right? I don't know if that's, like, allowed. But that could, like, actually, yeah. That could, like, hypothetically get you a bounded, or have your function be bounded. Additionally, you could have, yeah, I think those are the two main areas that I thought of. Okay, let's see. Function is bounded on domain D if there exist real numbers m and n, or lowercase m and capital M, such that lowercase m is less than or equal to f of x, and f of x is less than or equal to capital M for all x. I think this is like set membership, like for all x in D. Okay, yep. That is correct. Okay, so we're back up here. Okay, if there exists real numbers m and m, Oh, okay, okay. So it seems what they're saying is like for any given. Oh, okay, yeah, okay, this makes sense now. So this is literally just what we've described earlier. So it's saying for any x within our domain, which I assume would be negative infinity to positive infinity, we're going to have like f of x be greater than little m, and it always be greater than little m, and f of x will always be less than or equal, or sorry, greater than or equal to and little m, and f of x will always be less than or equal to big M. And that's for all x's within our domain. Okay? And then the function's range, the function's range is contained within the closed interval of little m to big M. Okay, so, and it also could be just bounded above and bounded below. Okay. 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 Oh, I guess another one would be functions like trigonomic functions that like oscillate back and forth rather than increasing in their output. Okay. Yeah, we'll just keep it. We'll just keep it. I'm just wondering if I should keep in calculus, but I think we're chilling. Okay, and then we'll just do the same for upper bound. Okay, oops. Perfect. Nice. Okay. I think we are doing pretty good here. So, we understand boundedness. Don't need that anymore. And I think actually we'll probably just end there. We'll revise my question number 2. And then we'll just continue from that point. And I think our next session will be on... Oh, will be tomorrow. Yeah, it's only Tuesday. Sweet.